So welcome to my channel. I'm Soikat Ghosh and I'm going to discuss about today's topic is conductance. So conductance is the current carrying capacity of a solution. Okay. So it is actually the reciprocal of resistance. That means conductance of a solution is 1 by resistance. Not only solutions, conductance is solution only applicable ta noy. It can be also applicable in case of solids, metals, non-metals, etc. etc. But in this chapter we are interested about the conductance of solution, electrolytic solution. Okay. So next, so conductance is 1 by resistance. Now the types of conductance. There are two types of conductance. That is, one is specific conductance and another is equivalent conductance. Now the unit of conductance. Unit of conductance is I have told that the conductance is the reciprocal of resistance. So unit of conductance is 1 by ohm, as the resistance, the unit of resistance is ohm. So 1 by ohm, that is ohm inverse. We can tell it mho, M-H-O, mho. It is denoted by omega sign, and it is in series unit, and the SI unit is Siemens. Okay, SI unit is Siemens. So the relation between omega and Siemens is 1 by 1 omega is equal to 1 Siemens. There is no multiplicative factor. Okay, the unit is same but the name is different. The next one is specific conductance. So the specific conductance is the resistance of electrolytic solution enclosed between two electrodes depends on length of a liquid column, and the second one is cross-sectional area of the liquid column. Resistance. So the resistance of an electrolytic solution. When a solution is carrying electricity, so there should be some resistance in the solution due to the ions, maybe another things. So this resistance depends on two factors. You can watch here that R is proportional to L by A, directly proportional to L and inversely proportional to the cross-sectional area. Okay, so by removing the proportionality sign, we can get a equal sign and a constant. This is specific resistance. This is the specific resistance or resistivity. L is the length of the liquid column and A is the cross-sectional area of the liquid column. The next one, specific resistance is this specific resistance is a constant term. We got as a constant it here, and this is independent on R and L and A. So specific resistance is a constant and independent on resistance, length and cross-sectional area of the cell. And the reciprocal of specific resistance, that is 1 by rho, is called the specific conductance. It is denoted by Kappa. There is the Kappa. You can see in the picture 1 by rho is equal to Kappa. This is a capital. This looks like a capital K. This is called specific conductance. So specific conductance definition: it is the conductance of unit cubic solution or one series solution. How can it be established? Right. See that 1 by rho is equal to 1 by R into L by A. From where the equation comes? There. R is equal to rho L by A. the next line is 1 by rho 1 by r 1 by rho is equal to 1 by r into L by A here. So 1 by rho is kappa, 1 by r is L, that is mho, that is conductivity, it is denoted by L, and L by A it's fixed. So specific conductance is kappa equal to mho into L by A. Now if L is equal to 1 and A is equal to 1 semi square, then kappa is equal to L. So kappa can may be defined as it is a conductance of unit cubic solution or 1 cc solution enclosed between two electrodes which are apart by unit distance from each other. Unit cubic solution, L into A, it is the volume, so we can tell it as a unit cubic solution, and 1 into 1 unit cubic solution and or 1 cc solution enclosed between two electrodes apart by unit distance, that is L is equal to 1. So when L is equal to 1, A is equal to 1, kappa is equal to mho or conductance of the solution. Okay. Next is unit of kappa. Kappa is equal to L means conductance into L by A. So conductance is ohm inverse, L semi square. So unit is ohm inverse semi inverse, mho semi inverse. This is CGS unit. SI unit is Siemens meter inverse. The next one is cell constant. Now what is the cell constant? You can see here kappa is equal to mho or L into L by A. This L by A is the cell constant. Unit of it is semi inverse or meter inverse in SI, in CGS and SI respectively. So definition: cell constant is the ratio of the distance between the two electrodes and the cross-sectional area in a conductivity cell. It is a fixed quantity. Cell constant is a fixed quantity for a particular cell. Okay. It does not depend on the nature of the electrolyte used in the cell, is using in the cell. Okay, and temperature, etc. etc. It also depends on the distance between the two electrodes and the cross-sectional area of the electrodes. Now, how can we measure the cell constant for a conductivity cell? Measurement of a cell constant for a conductivity cell. We know that cell constant is equal to L by A. So now to determine the distance between the two electrodes in a cell and the cross-sectional area, it is very difficult. So now to measure the cell constant, we have to take another indirect process. What is the indirect process? We know that the specific conductance means we can fill the cell. আমরা একটা সেলকে fill করব with a known specific with a solution of known specific conductance. We can fill a cell with a solution of known specific conductance. একটা known specific conductance এর solution দিয়ে একটা cell টাকে ভর্তি করব. Now measure the conductance of the solution. So we can measure the conductance of the solution from this. Now from this equation in below, the kappa is equal to L into L by A. We can measure L. We know kappa of the solution. Now from this equation we can get the L by A. This is the indirect process. Okay. Next one is factors affecting kappa. Kappa, it is directly proportional to the number of ions, velocity of the ions in solution, and temperature and concentration, and it is inversely proportional to the viscosity of the solvent and hydration number of ions. And specific conductance and concentration of the solution. Normally the concentration of solution depends on two opposite factors: concentration of the solution. Conductance of solution depends on two opposite factors. What is these opposite factors? One is velocity of the ions and number of ions per unit volume. The first one is velocity of the ions. If the velocity of the ions increases, then the conductance value also increases. Okay. Now, if the number of ions per unit volume increases, here two factors can occur. First one is number of ions per unit volume increases, so number of ions increases, so the current carrying capacity also increases, so the conductance may also increase. And the opposite factor is, if the number of ions per unit volume increases, so the distance between the two ions decreases, the interonic attractions between the two ions also decreases, so the velocity of the ion is disturbed by the another ions, so the velocity of the ions decreases with increasing the number of ions and the interonic attractions between the ions. Okay, so there are two opposite factors of increase of number of ions per unit volume. Now, in case of specific conductance, it is seen that the number of ions per unit volume increases and the specific conductance increases with the number of ions per unit volume. That is, we have to keep in mind that specific conductance value always depends on the number of ions per unit volume. Okay, it has been observed. Now for strong electrolyte, solution, what will happen? For the strong electrolytic solution, the number of ions per unit volume decreases with increasing the dilution of the solution. If we dilute the strong electrolytic solution, the number of ions per unit volume decreases, as strong electrolytic solutions are completely dissociated at any concentration. Strong electrolytes. What is the example of strong electrolytes? Strong electrolytes are KCl, NaCl. These are the all example which is completely dissociated at any concentration, that is alpha is equal to 1. The solution who has the alpha value is equal to 1 is called strong electrolytic solution. So for the strong electrolytic solution, alpha value, kappa value, means the specific conductance value, decreases with increasing the dilution of the solution or decreasing the concentration of the solution. As we know, as we tell that in the previous slide, that the kappa always depends on the number of ions per unit volume. So with dilution, as the number of ions for the unit volume per unit volume for the strong electrolytic solution decreases, so the kappa value also decreases. So kappa value for the strong electrolytic solution decreases with dilution or increases with concentration linearly. Next, weak electrolyte solutions. Now there is some complicated things for the weak electrolyte solution, because for the weak electrolyte, we know that on dilution, the number of ions per unit number of ions increases, as weak electrolytes are not completely dissociated at any concentration. So there are two opposite factors. With dilution, the number of ions per unit volume may decrease, and here the dissociation, here for the weak electrolytic solution, number of ions per unit volume increases due to dissociation. Means ডাইলিউশনের সঙ্গে সঙ্গে উইক ইলেকট্রোলাইটিক সলিউশনে যেমন প্রত্যেক মানে ইউনিট ভলিউমের নাম্বার অফ আয়ন ডিক্রিজ করার কথা, আবার যেহেতু এটা উইক ইলেকট্রোলাইট তাই ইউনিট ভলিউমের নাম্বার অফ আয়ন ইনক্রিজ করার কথা ডিউ টু ডিসোসিয়েশন। দুটো অপোজিট ফ্যাক্টর কাজ করছে এখানে। সো it has been observed that with dilution the increase of number of ions due to dissociation is very very less for weak electrolyte. So we have to take the dominant factor is the number of ions per unit volume decreases for the weak electrolyte solution. So the final result is the number of ions per unit volume decreases with dilution for the weak, both for weak and strong electrolytic solution. So kappa value always decreases with dilution or increases with concentration for both strong and weak electrolyte solution. Now, now the graphical representation of kappa and concentration. If we plot kappa in the y-axis and concentration in the x-axis, we can obtain a straight line. Sorry, not a straight line. This is a somehow curved line passing to the origin. Okay. This is a smooth increase of kappa value with concentration. This graph shows the smooth increase of kappa value with concentration. Okay. The next topic is specific conductance does not depend on the cell constant. Okay. I have told earlier that specific conductance value is a constant value. It does not depend on R, L and A. So this value is fixed at a particular temperature and a particular for a particular cell. That it depends is conductance. The value of conductance means rho is equal means R is equal to rho into L by A. You can see in the previous slide the you can see the previous slide the kappa is equal to L into L by A. Now kappa to R is conductance. R is in kappa is independent on R, and kappa is also independent on L and A. Means in which cell it is taking is also independent. So kappa is independent on cell constant. Hope you can understand this. So that's all for today. Thank you.